So thank you very much for coming to Jason's thesis defense. Jason has been here for quite some time, and he graduated from UCLA, bachelor degree in chemistry. And during his undergraduate study, he did a thesis, a research an undergraduate student with Saratoga. And he also spent a summer here at UCSB, and that's how he fell in love with our place, and he decided to come here for his Ph.D. And one thing I have to mention, what unique about Jason compared to many of you guys sitting here, that during the past 5 years and a half, he faced many different challenges in terms of his health, family, but despite all of that, he overcame all of that those barrier to stand in front of you today. So and he constantly take criticism very well from me, from a committee member, and try and hopefully he can convince you today, Fred, that he had gone very far from the day that he took the candidacy exam or the day that he entered UCSB to where he are right now. And I can see the thesis work he talked about today, I can give some idea. And he would go out there, he would learn many techniques by himself and make it happen. So with that, I let him show you what he has done.
Thank you very much, Dr. Coach. And I just want to thank all of you for taking out time today to listen to my presentation. My community members, Dr. Nguyen, I couldn't have done this without your continued support. And of course, my friends and family, for everything and always supporting me throughout the whole process. So to begin, my presentation today is on Exciton diffusion link and solution process, small molecule organic solar cells. And just for the people who don't have a background in this, I just wanted to say, what is the motivation specifically to study organic solar cells? Well, simply, it's a renewable energy source, and we need that. We need something that will last for a long time. In addition, it's cleaner than fossil fuels, that it doesn't produce pollution. And then in addition, it has the potential to be fabricated at a lot lower cost than inorganic solar cells, which often are very expensive because it requires high purities and high temperatures to make these solar cells. So the next question is, how do these organic solar cells work? So the basic device operation is 4 different steps. Sorry, the number kind of got cut off here. Wow, the color's really bad. This is actually supposed to be green. Okay, anyways, so the solar cell is basically composed of an active layer, which is an acceptor layer, and a donor layer. And in addition, it's surrounded by 2 electrodes. One is the aluminum cathode and the anode ITO. So this is indium tin oxide. It's transparent and conductive. And finally, we have our substrate. So the first part of operation is where we have a photon come into the material. It could be absorbed by either the acceptor layer or the donor. Let's just say, for example, it's absorbed by our donor layer. What happens is that when a photon gets absorbed, we have this excitation of an electron to a higher energy level, and what it leaves behind is a hole. And these electron and holes are coulombically bound together, and this is called an exciton. And the attraction is so strong actually that this exciton, this electron and hole, will diffuse together. And that is the second process. Once we form this exciton, it will have this random rock diffusion. So finally, hopefully, it reaches the interface between the acceptor and the donor. When it reaches that interface, the acceptor, often it's a ball of foolery, it actually has a strong affinity for electrons. It can accept that electron and steal it away. And then that gives the driving force for this charge separation, where we now have the electron in the acceptor phase, hole in the donor phase, and then finally, we have a drift of the electron in the acceptor phase to the cathode, drift of the holes to the anode, and then finally those would combine to complete the circuit to give you power. So that's basically the operation of a solar cell. And I actually want to show you what one looks like. So this is a funny story because when I teach my classes, I like to talk about my research to the students. And then one student actually told me that there's actually this company that you could basically, you could actually have them mail you a solar cell. So if I find that later, I'll actually pass it around, but you can actually have them mail you a solar cell. And it's actually this really thin flexible solar cell, which you could actually test yourself, and it just shows that there actually are companies that are making this, and it's actually a reality too. We just gotta work on it a little bit more. So these are basically 4 main projects that I worked on during my PhD. The first project, I basically had 5 different chemicals, and I studied how slight chemical and incremental modifications affect everything from the packing, the morphology, the absorption, the mobility, and then ultimately how that related to the device performance in a solar cell. What I then did is I used some of those same molecules for my next project, project 2, which was to study how does these same chemical modifications impact fundamental properties like this exciton diffusion length. In addition, I wanted to compare different techniques to measure exciton diffusion length, because there's many different techniques, as I will elaborate later. And then after that project, I wanted to kind of delve deeper into exciton diffusion length, like what is actually the mechanism of exciton diffusion. So in this project, I used temperature studies, and I measured the exciton diffusion length at different temperatures. In addition, I wanted to look at how processing condition affects the exciton diffusion length. And then finally, the last project, I compared a couple different molecules which have previously shown to have high performance in organic solar cells. And I wanted to see what is the exciton diffusion length in these materials. Are they any different, or are they about the same? So due to limitations on time today, I will only talk about the second and the third project. So project 1, systematic study of exciton diffusion length in organic semiconductors by 6 experimental methods. So again, just want to say that I'm focusing on the step where we have just exciton diffusing. And we want to basically increase that length, because you can imagine that when light is being shined on this film, there's excitons being generated everywhere. But if the exciton is generated down here, it has not too much of a probability of reaching this interface if the diffusion length is very short. So our goal is to actually increase the length that this exciton can travel. So in summary, what we want to do is we want to find the relationship between chemical structure and exciton diffusion length. If we can find this relationship, we can hopefully know what chemical modifications will lead to a larger exciton diffusion length. So, of course, we can actually study this already with literature, because there's been a lot of publications of exciton diffusion lengths in different materials, but there's challenges with that, because, for example, you have 2 different publications, 2 different compounds. Let's say we want to compare the exciton diffusion lengths of these 2 compounds. One was 5, one was 10. Well, this sometimes is challenging because these chemical structures could be very different from each other. They could differ by a number of chemical modifications. So it's hard to tell how one chemical modification impacts the exciton diffusion length. In addition, it's further complicated because there's so many techniques to measure exciton diffusion length that it's a very good chance that they use a different technique. So that makes it even harder to compare the 2 molecules to one another. So those are the 2 difficulties of using current literature to study exciton diffusion length. And with that gap in literature, I developed a couple of different guiding questions for my research. The first guiding question was, how do different techniques compare with each other? So I want to compare different ones, compare the fabrication, the measurement, and the analysis. In addition, at the same time while doing that, I want to compare how does chemical structure impact exciton diffusion length for 3 compounds which are very similar. They only differ by slight chemical modifications. So with that, I developed a project proposal, and it's to compare 6 different techniques to measure exciton diffusion length in a class of diketoperol small molecules. So the first choice was what material I would use. So I chose these 3 small molecules because they have, very slight but interesting chemical modifications. For example, when you go from B to A, it's supposed to be red, B to A, the conjugation is reduced. What I mean by that is that the number of thiophenes on the back is reduced by 2. So this one has 2 thiophenes, but this molecule A only has 1 thiaphene. So we reduce the conjugation length. And that affects a lot of things actually, because I previously studied these materials in terms of performance and morphology, and I found that as you decrease the conjugation length, you not only affect optical properties, but you definitely affect the morphological properties, like it becomes more crystalline. In addition, I also studied how increase in molecular bulkiness affects the packing. So the difference between the black structure, or B and C, is that we've converted the linear alpha chains to a branched ethyl group. And what this does is that makes the molecule bulkier, and it prevents it from packing in film. therefore, this film is actually often amorphous. It is kind of randomly packed in a film. Okay, so then I did some literature search to see what are some techniques to measure exciton diffusion length. And there are a lot, actually. And these are 6 I chose. There are actually a few more that are there, but these are the ones I chose to analyze. And actually, when I first saw this, it was kind of daunting. You know, each one had a very unique fabrication, measurement, and analysis. And I had no background in this. In addition, there was no one in my group that had previously really studied exciton diffusion length. There was one person who kind of briefly tried it out. His name was Brett Walker, but not thoroughly. So it was actually very challenging for me to kind of approach this. But nevertheless, I moved forward, step by step, and through trial and error, I worked through it. And what I wanted to present today is 2 techniques on how to measure exciton diffusion length. So I'll tell you about the first technique and also the 4th technique down here called quenching. So the first technique is called steady state photoluminescence with surface quenching, or SSSQ. So the first step is fabrication. Oh, geez, the colors are all messed up. Anyways, so what we first want to do is make a layer of our film. So we dissolve our organic material in an organic solvent, and we deposit it with a syringe on a substrate. We then put it on a motor that spins. So this spins at a specific rate, and the rate that this spins will determine the thickness. In addition, this thickness is determined by the concentration of our solution that we start off with. We then have a very consistent organic layer on our substrate, and what we then want to do is add a quencher. So the quencher we use is C60. As I mentioned earlier, this accepts electrons. And what we do is we actually cover half the film, and we evaporate the C60 on our substrate. And what this does is that we have half the substrate that has the quencher and half that doesn't. So it kind of reduces the amount of material we need and actually makes the study more consistent because we can compare the same thickness on both sides with and without the quencher. And then the final form of how these films look like is basically, it looks like 2 pieces of glass glued together. This is like epoxy. This is actually really important because a lot of these organic films are actually very sensitive to oxygen. If you excite them with light and you expose them to oxygen, it's very likely that they're going to photodegrade. And that might change the chemical structure and reduce the lifetime of these materials. So what we then do is we change the concentration of the solution, and by doing that, we actually are able to produce different thicknesses of the organic layer. So you can see we have thick films, and then as the film thickness decreases. So I wanted to kind of take a step back and kind of talk about what's actually happening in these films. What happens when we actually excite them with light. So you see here, this is the regular film under room light, but if we put them under UV light, you begin to see this fluorescence. And it's kind of hard to see because the color contrast is weird, but the right side is actually dimmer than the left side. And the reason why the right side is dimmer is because the right side has this layer of C60. And what this does is that when excitons are generated near this C60 layer, there's a good possibility that they will reach this quenching interface and be quenched. And therefore, they would not be able to relax. Because one of the processes that excitons can do is that when they relax down to the ground state, they can emit light. So these excitons that are quenched at the C60, they have no possibility of even a chance of emitting any light. Therefore, the amount of light emitted by the right side will be less compared to the left side. And we can actually see that in the spectrum. So when the exciton relaxes back down, it actually emits a couple of different wavelengths based on the energy levels in the material. It emits a different wavelengths here. So you can see we have most of them emitting around 700 nanometers. And if you compare the 2 sides, we can see the area underneath the curve is different. And what that means is that there's less total number of photoluminescence from the right side compared to the left side because the right side is being quenched at C60. So now going on to the measurement. So what we do is we use a argon laser as a wavelength of 457, pretty close to UV light, and we excite one of the sides. Let's say we excite the side without the quencher first, and we output a number of different wavelengths. What we then might do is also add a filter because this UV light is actually quite strong. Some of it won't even be absorbed by this film and will just pass right through. And we don't want that to go all the way to the detector because the detector is actually very expensive and very sensitive. So we don't want it to ruin our detector. So we filter out the UV, and we only record the fluorescence that comes from this film alone. We don't want any light from the detector. And And then, as I mentioned earlier, we get the spectrum, which you have here. And you could get, if you measure the other locations where there's a quencher, you would get a spectrum where you have a little bit less due to quenching. So now the next question is, what can we do with this data? Well, one thing you can do is calculate the quenching efficiency. And as I mentioned, you have these two different locations, and you could use this formula to calculate the quenching efficiency. Basically, what this is the integral of the PL with the quencher over the integral of the PL with the pristine. A way to simply think about that is that it's only basically the area of the blue, the film with the quencher, over the area without the quencher. So let's say, for example, you had a material that had a very, very long exciton diffusion length. In this case, all the excitons generated on the side with the quencher will be quenched, and your photoluminescence from here will be very diminished, because none of them are emitting, they'll all be quenched. And in this case, this would approach 0, this whole thing would approach 0, and our quenching efficiency would be 1, basically. So higher exciton diffusion length, higher quenching efficiency. And that's how the two are connected. So now the question is, how do we connect this measurement with a model to determine what the exciton diffusion length is? Well, what we first have to do is figure out what is the exciton density profile in this film. And actually, it's not homogeneous. You would think that you shine this film and excitons are generated equally throughout, but in fact, they're not. And the reason is because as light enters this film, it actually gets reflected at each interface because there's a difference in index of refraction of each of these materials. And it actually reflects at itself, so it can actually constructively and deconstructively interfere with itself, creating these patterns. Further, that optical field could be absorbed by the organic material, decreasing the field. And then finally, with that absorption, you create this absorption profile or exciton density here. And this is kind of like the initial condition, the initial population of excitons. And what we want to do is see is what's going to happen now. You have this initial population. What happens? Well, how excitons move is through diffusion. An example of diffusion is when you add a dye into water. The dye starts off very concentrated and it diffuses out. But what's interesting about excitons is that not only does diffusion occur, but it also disappears. When you add dye into water, let's say a red dye, the water becomes pink. But in my case, the water will become clear again because the dye itself kind of disappears. That's kind of like saying that excitons will kind of quench itself. So to model this diffusion, we use this partial differential equation, which basically is able to predict how these excitons will migrate from higher concentrations to lower concentrations, and how many of them will reach this interface, which is the quenching interface. And therefore, what the model does essentially is that it chooses different exciton diffusion lengths, and it predicts what the quenching efficiency would be for each of those. So how I like to think about it is that there's this little guy in the computer, and he's kind of comparing a model with the measurement. And let's just say, for example, that we did the measurement, and we calculated quenching efficiency, and we got a number of 0.5. So that is our goal. So now the guy does in the model is that he wants to say, okay, if you have these different exciton diffusion lengths, these are the different quenching efficiencies you would have. And he matches the quenching efficiency with the exciton diffusion length. And that is basically how they merge the model with the measurement, and you obtain the exciton diffusion length with this technique. So finally, the verdict on this technique. The fabrication requires many films, 10 to 20. I actually reduced the number of films because I evaporated only on half with C60, so I was able to cut it by half. But really, you have to probe a lot of different thicknesses, from 10 nanometers up to like above 50 nanometers. So that requires a lot of material, a lot of time. In addition, I didn't discuss, but it's actually very difficult to find an efficient and robust quencher. So before using C60, I actually tried a lot of other materials because I wanted to have an interface that was firm, strong, and efficiently quenching. But a lot of materials like TiO2 and polymer receptors, they just didn't work as well as C60. So finally, I settled upon C60. In terms of measurement, it's actually quite demanding too. What I didn't mention is that when we measure these films, you can imagine that we have to hit these films very normal. If we were to hit them at an angle, some of the light will get reflected, and that would appear as quenching. So it's very important that we hit all these films very normally, and that requires a lot of optical alignments accurate. In addition, I did mention that there's also a lot of other measurements that you have to do. You have to make sure that you know the exact thicknesses of these films, and you have to know the optical concept. You have to know the index of refraction and the Exciton coefficient, and that requires additional modeling with spectroscopic lipsometry. Finally, the one good thing, this is supposed to be green, this is supposed to be red, but the one good thing is that it does fit for the Exciton diffusion link directly. You are fitting to that number directly, so you're measuring that. Other techniques, which I'll discuss after, actually figure out a different value and then calculate the Exciton diffusion link. So with that, I struggled through these two, and I finished these two, and I wanted to find another technique that was more robust, easier to do for a bigger study, because I didn't want to just keep comparing techniques. So luckily, I was able to collaborate with Olex and travel to Netherlands, and he actually had another technique that was really nice, where you could actually measure the Exciton diffusion length with a Monte Carlo simulation and measure it in bulk. And I will describe that technique. So bulk quenching with Monte Carlo simulation. So the preparation is similar. We just use spin coating, but now we add in an extra material. So these balls are PCBM. It's very similar to C60, but we've added some additional groups that makes it soluble in organic solvent. So we mix different concentrations of our organic semiconductor with the PCBM, and we're able to produce different films with different concentrations of PCBM. The next thing we do is we do our measurement. And this time we have a different type of laser. We have a titanium sapphire laser that emits at 400 nanometers. The main difference between the other lasers is that this one emits a very short pulse. It kind of pulses the film. So at time 0, you have this population of excitons, and then they'll gradually decay. So as I mentioned earlier, when you have excited excitons, they can emit at different frequencies. But what we want to do is we just want to record one wavelength. So we'll use a monochromator to just select one of these wavelengths, and we'll turn on the detector. And this detector will not, instead of recording at different wavelengths, it'll actually record as a function of time. It will just sit there and wait as these excitons arrive. And what will happen is that we get to have these points appear on this graph where you have at different times excitons appearing in the detector. And if you were to connect all these plots together, it would form this curve here, which is basically an exponential decay. And that can be fitted by a simple decay formula. So now the question is, how do we calculate the quenching efficiency of this curve? Well, let's first look at the plot for a film without any PCBM. Like I mentioned earlier, we'll have this exponential decay curve, and we'll have an area underneath. But if we were to add some PCBM, what we see is that there's a more rapid decay of the excitons, basically because there's a less likelihood of longer-lived excitons because they're more likely now to reach a quencher. So therefore, we cut down the exciton lifetime. And to exaggerate that a little bit further, we could show that if we further increase the exciton concentration, the PCB concentration, the lifetime decreases further. So again, using the similar formula as last time, where you have the integrals with the quencher over without quencher, we could calculate what's the quencher efficiency of each of these films. So it's just basically the area with the quencher over the area without. And this is the film without any quencher, the control you can think of. And what you see is that when you have more quencher, you have a higher quenching efficiency compared to when you don't have as much of a quencher. So we could do this for a number of different films. We could prepare films with different concentrations of PCBMs, and each of those we could calculate a quenching efficiency. And this is the kind of the plot that you would get by doing that. So the next question is, how do we connect this measurement with a model to determine the Exciton diffusion length? So this kind of symbolizes the Monte Carlo simulation. And what a Monte Carlo simulation is basically a program that runs multiple trials. It's kind of a random process. And that's how it basically determines and fits for the Exciton diffusion length. And to give an example, it could basically run a simulation of Exciton diffusion for a couple of different situations. Let's say for low diffusion, medium diffusion, and high diffusion. For a low diffusion, not many excitons will be quenched, so you should have this pretty broad curve. But when you have a very high diffusion coefficient, these excitons are more likely to be quenched by a PCBM, therefore the lifetime will be cut down, and you would have this trend where you have low quench efficiency to high. So finally, we come back to the little guy in the computer, and what he wants to do is compare the measurement with the Monte Carlo method. So let's say, just for example, that you do the measurement and you get a quenching efficiency of 0.5. So that is the goal to look for. What you then do with the Monte Carlo is that you simulate for different diffusion coefficients what the quench efficiency would be. And then you match the two. So you see that 0.5 matches 0.5 here, which corresponds to a diffusion coefficient of 10 to negative 4. You can then plug this into the simple equation for an exciton diffusion length. Here, D, and the T is the lifetime, which can be just measured from the pristine film. And finally, you can arrive at an exciton diffusion length. And this is what I meant earlier, that we're not directly measuring the exciton diffusion length, we're actually determining D, and then figuring out what LD is after that. So that's kind of the difference compared to the other technique earlier. So finally, the verdict on this gold quenching method. The fabrication is pretty nice because it could actually be done with as little as 8 films. And the method is actually very robust. To spin coated blend film is a lot easier than preparing these bilayer films. It requires less material and less procedures, less steps. In addition, the measurement uses time-resolved spectroscopy. As I mentioned earlier, with the steady state, it's actually extremely sensitive to orientation of the film. But time-resolved is a little bit less sensitive, so it actually makes the measurement a little bit more accurate for our exciton diffusion length. And then finally, the analysis. It's also nice because this model can actually measure multi-exponential decays. There's some methods that only could work with single exponential decays. So I discussed technique 1 and 4, and I don't have time to discuss other techniques, but just rest assured that I did go through these. I actually collaborated with a lot of groups, like one in Ireland, and we went through all 3 materials with all different techniques, comparing the fabrication, measurement, and analysis. It's a very comprehensive work. And what I just want to summarize now is the final result of a graph that puts everything all together. So what you see here is 3 different columns. Each of these columns represents a different material. The one with the short conjugation, medium, and the bulky molecule. And then what we have on the y-axis is different exciton diffusion lengths. And each of these symbols represents a different technique. So one thing we can do first is compare techniques. And one way we can do that is just look at one material with different techniques. So let's start with this material here, the bulky group. We can actually see that they actually kind of lie all pretty close together. They're about within the error of their values. So this would seem to indicate that, okay, the techniques are very similar. No matter what you get, you'll get the same result. But then, if you just look at this material here, the smaller one, now we get this larger distribution of exciton diffusion length. And this was very confusing. Like, we have the same material, but we're getting different exciton diffusion length, and we're getting a larger error. And the reason why that is because this material is very crystalline, a lot more crystalline relative to this one. This one's amorphous. And when you have crystalline materials, they're extremely sensitive to how you process them. How long you wait for them to dry, how fast you spin them, what the ambient temperature is. Anything to change that morphology. And that morphology will change what exciton diffusion length you will measure. So the conclusion is that, if you're going to work with crystalline materials, you got to be careful about comparing different techniques. It's maybe only good to compare amorphous materials between different techniques. So the next thing we could do is kind of compare, now we compare techniques, let's compare chemical structure, these 3 together. And what we see is there's actually this kind of trend downwards. And one thing that we found is that this actually correlates pretty well with the crystallinity. We did some X-ray diffraction measurements, and we measured the order in the film. And we see that this trend correlates with the order in the film. And then, so basically, to summarize, this work, the main contribution was that it provided the research community with a comprehensive work that compared the fabrication, measurement, and analysis of different techniques. So what that enables is that a new researcher could kind of come in and say, okay, this is what I need in terms of instrumentation, and this is the type of material properties that I might want to consider if I want to do this process. In addition, my work showed that the Exciton diffusion length should only be compared between the same technique just to be safe. And I also found that, from experience, the surface quenching techniques are quite demanding. They have a elaborate fabrication, multiple measurements, and a number of assumptions in the process. However, the bulk quenching with multi-color simulation is actually a really good technique because it can be done very quickly, and you can do a lot of different systematic studies. And finally, we find that the Exciton diffusion rate correlates with the degree of molecular ordering. So if I had more time for this project, some future work questions I might ask is, how does the analysis procedure differ between the works compared mathematically? How does the actual math calculating the Exciton diffusion rate compare? And actually, this is actually being done by one of our collaborators, because for two of the projects I worked with, I didn't have the expertise to do the analytical modeling, so I collaborated with Professor Carlos Garcia. And they actually are working on now the mathematical model. And some of the preliminary results actually show that some techniques overestimate the diffusion coefficient compared to others, just based on mathematical calculations. Another question I might ask is, how does the photocurrent method compare with the photoluminescence techniques? So all the techniques I studied in this specific work was all for materials which are able to emit light. But there are actually a lot of materials that aren't able to emit light. And for those materials, the way to still calculate the Exciton diffusion length is to measure the current, because the more excitons that reach that interface, the more current you would generate. So you can calculate it that way too. And then finally, another question that might be interesting to probe is, can Exciton diffusion length actually be measured in a bulk heterojunction film rather than just a bilayer or PCBM film? That's usually the conditions that we probe. But most solar cells are actually a bulk heterojunction. What that means is that the two materials are intimately mixed together. So now that I finished that project, I kind of knew, okay, a good technique to study to use is Monte Carlo. So I could use that technique to do another study. And one I wanted to probe was the temperature dependence of Exciton diffusion length in a small molecule semiconductor with or without additive. And I wanted to give some background for that motivation. So in the field of organic semiconductors, there's actually a lot of studies that have shown that when you process a film with a high boiling point solvent, such as a dialoctane, there's an increase in the current generated. For example, this blue going to this yellowish goes from 7 to 13. And most of the studies actually study how that affects charge transport and charge generation. And there's no studies that have been studied about how that affects the Exciton diffusion rate. So that was one of the questions I wanted to answer. How does that affect that part? Another motivation for this study was that another publication by a colleague showed that when you compare the Exciton diffusion rate for different materials and a calculated trap density, you find this trend where when you have a larger concentration of traps, you have a shorter Exciton diffusion rate. So what I wanted to see is that, does processing affect the number of traps, and how does it kind of connect with the Exciton diffusion rate? So big picture wise, I want to find out the relationship between processing Exciton diffusion rate and also trap density with the Exciton diffusion rate. And then from this, I developed 3 guiding questions. One was, how does the mechanism of Exciton diffusion rate in small molecules compare to polymers? Another question was, how does the processing conditions impact Exciton diffusion rate? And finally, what is the relationship between Exciton diffusion rate and the Exciton trap density? And the project proposal was basically to use the bulk quenching method plus this bulk quenching Stern-Wohler method. And I didn't discuss this technique, but what's nice about this one is that you can actually calculate the Exciton trap density in your film. So that's why we want to do those two in parallel. And we want to compare these two with temperature dependence, measure the Exciton diffusion rate at different temperatures, and also with different processing conditions, with and without the DIO. So the first step was fabrication. So we have our quartz substrates, and we spin coat them. And these are actually quite small. These are actually smaller than a penny, which actually kind of made them difficult to work with. And the reason why we had to do that is because we didn't have a lot of material. And some of these materials are actually very expensive and require a lot of work to synthesize. So we spin coat it, and And then from experience, I learned that you actually should scratch off the edges. You want to get all the way down to the glass. And the reason is because the next step is you want to apply some epoxy around the edges. And you want that epoxy to go all the way down to the glass where it can get hold. If it grabs onto the organic layer, it'll just kind of peel right back off. You want it to get down to the glass. And then finally, you put another substrate on top to encapsulate it, and now you're enclosed. And this, I have to remind you, is all done in a glove box filled with nitrogen, so there's no oxygen to be in this film upon encapsulation. So we fabricated a number of films, and then we had this setup where we could measure 3 films at a time. And this was, in a way, a little bit inconvenient, because we have to cool down the temperature all the way down to 4 Kelvin. If we only can measure 3 at a time, that requires a lot of back and forth, going back to room temperature, back to cold, back to room, if we want to probe a lot of different conditions. And just to give you an idea of the setup, we had the laser set up back here, and we had to actually order this helium tank. And this is actually quite expensive. This was like about $560 for this tank. And the problem with this is that not only is it expensive, but it kind of evaporates. And when you get this, you have to kind of do the experiment right away. What we also had here in our setup is that we had a flow rate controller. This allowed us to manage the rate of flow into our setup so that we can control the temperature. So we could either cool it down or heat it up. And this was the cryostat, where basically we put our film in here, the 3 that I showed you, and we measured through here. What's also important is that we use a cryo pump to pump down the walls here. We actually want to create a vacuum around the walls because the inside will be very cold, 4 to 10 Kelvin at one point. And what can happen is condensation can build up if you don't have a good insulation layer around this cryostat. So after long hours, we also actually had this picture. This is actually functional. We weren't just making giant helium balloons. This is actually called a bladder. And what this does is that when you push some warm air into this dewar, it kind of heats up this liquid nitrogen, it causes it to expand. Therefore, you kind of get this process going to start cooling down your system. Before that, I wanted to take on to a funny story is that, during that process, me and Oleg had to work many hours. I think we were working like at least 15 hours a day. We'd go take lunch, come back, do the measurement, and then a funny story is that one Sunday we were doing the measurement and we started seeing all this condensation building up. And we realized that it was because one of the O-rings had a crack and it was like preventing a good vacuum. So we had all this condensation building up. So what we did is we actually drove down to Kmart and picked up a little $10 fan and just put it next to it, and just for that day at least we were able to kind of drive off the condensation, just continue the experiment. And I just thought that's funny because we have this $560 nitrogen tank and these expensive equipment, and we're using this like little cheap little fan. But anyways, so now we have this. We finally had all our results. I don't want to go through all the calculations, even though it took a long time, but I just wanted to summarize what our result was. And what you see here is 2 different graphs where we have temperature on the x-axis and the diffusion coefficient on the y here, and the diffusion length here. And what you can quickly notice is that there's actually 2 regimes. You have one regime from 300 around room temperature to about 150 Kelvin, and another regime from 10 to about 150. And what you see in this regime is that we have this increase in exciton diffusion length as you increase the temperature. And what that indicates is that it confirms that the mechanism of exciton fusion is actually temperature activated. As you increase the temperature, you increase the amount of excitons that are able to diffuse. It's a hopping process. In addition, this region down here shows that even at cold temperatures, when they don't have enough energy to hop, they can actually still diffuse. And in this region, the reason why they're able to diffuse is because these organic semiconductors actually have different energy levels. And as the exciton relaxes down, it can kind of go through these downhill migrations and diffuse a little bit further. But it's not very much, only maybe like 2 nanometers. And so what this kind of confirmed is that the mechanism is similar to polymers. But one thing that we did find out was kind of unique compared to polymers was that the amount of diffusion in this low temperature regime was actually quite low. The polymers was about like 3 times higher compared to this small molecule. So that was one interesting difference that we did find between the 2. In addition, in this study, we wanted to kind of compare the trap density. So using this equation here, we just plug in the diffusion coefficient that we measured, the pristine film lifetime, and the lifetime without traps, which we can measure from the solution. And we can then calculate what the trap density is. And what we find that's interesting is that when we add DIO, we have this decrease in exciton diffusion length from 6.8 to 4.9. And this is quite counterintuitive because we knew from previous studies that processing with DIO increased the crystallinity of the molecular ordering. So it kind of contradicted to our previous work and a lot of other works. In addition, what's also very interesting is that we found that the trap density increased from 3.8 to 10 to the 17 to 15 to the 10 to the 17. And basically that is about a 4 times order of magnitude increase in the trap density. So both of those results were kind of unexpected, but the nice thing is that it kind of raises more questions for future work. So just to quickly summarize, like polymers, there's 2 phases of exciton diffusion, the downhill migration and the thermally activated hopping. That's what we confirmed. And we found that downhill migration has a smaller contribution in small molecules compared to a polymer system. And we also find that processing with DIO leads to this reduction in exciton diffusion length and an increase in the trap density. And yeah, that's pretty much the vision. And then if I had more time to continue this work, some interesting questions that I might approach would be, what is the origin of these exciton traps? You know, is it actual molecules in there, or is it grain boundaries being formed? You know, what is quenching these excitons? Another question is, you know, what happens when these excitons reach these trap states? Are free charge pairs generated? You know, there. Maybe that could be a useful thing. In addition, you know, how is an exciton trap related to a charge trap? There's previous work that showed the density of charge traps is almost equivalent to the density of exciton traps. So the question is, are they the same thing, or are they kind of the same thing? How is that connection actually? So overall conclusions for the dissertation. My work basically cleared up the ambiguities between techniques used and also identified specific techniques which are useful, such as the Monte Carlo for systematic studies of exciton diffusion length. In addition, my work confirmed that exciton diffusion length is directly limited by these trap states. And finally, now we have like a clear roadmap and direction for future studies. So there's a lot of people I have to acknowledge through many years here and many collaborations. Basically, thank you very much for supporting me throughout all these years. I know it's been very challenging and the projects have been very frustrating, but thank you for continuing to support me and believing that I could get this project finished and completed. Arnold, who was the first person to introduce me to my first project, he gave me these materials to actually study, and he actually was there for me as a mentor and a good friend throughout the beginning and the end. Even before I came here as an undergrad, I knew him. It should be him. It's like a father. He kind of told me, how to be firm about research. And then Jinhua, he was also like the father of synthesis. And Olex, I have to do a lot to him. He really kind of mentored me throughout my last couple of years, and telling me how to do research even more systematically, and also giving me good discussions. Riley Rao was the undergrad that I worked with. He was very bright. We struggled through the bilayer quenching techniques together. Definitely Manani Toy, a former member. She was there to support me as a good friend when I first started. And Michelle Guy, who I also collaborated a lot with a couple of different projects. And there's some new members too, like Wei, a couple of new people that came in. But also a lot of collaborations with Netherlands. For the bulk quenching, I actually traveled to Netherlands and collaborated with Paulo and Antoine Lloyd. And then also the collaborations with I4 Samuel for one of the techniques called exciton annihilation. It's postdoc Zarifi. And also, of course, I want to thank all the design group members. Our many group meetings and discussions have definitely helped me a lot. And of course, my friends and families who came out all the way from different locations just to see me present today, and also just on funding from NASA Science Foundation and NSF Solar. And what you see here is 2 different generations. That's the old Quinn generation. This is the new generation, but I'm still the interface between. So with that, I just want to thank you for your attention. and also when you add a little bit of the actual layer.
Other questions? Alexander?
Well, if you look at the temperature-dependent data on the Exciton diffusion, so you see that there is a diffusion at low temperatures when the thermal topping is frozen, right? So can you think that this is due to Forster energy transfer because it's dipole-dipole should be dependent on the temperature?
Can you rephrase that again? Sorry.
Well, do you think that diffusion at low temperature can be caused by Forster energy transfer mechanism?
Yeah, that's definitely a possibility too. And that would kind of be something that we would want to tease out. What is the actual mechanism of this diffusion of the temperature? And maybe one way we could approach that is to kind of further modify the processing conditions. Because one thing we do want to see is actually, how is the density of states changing in these films as we process them? And we have to use other techniques to measure that. And I think actually that would be an interesting question too.
Any other question from the audience? So if not, that time Jason again, and I will ask the audience to leave the room, and you can hang out outside while